All right, let's get started. We are already done with the integration method for solving beam deflection problems, and we have seen its procedure on how it solves the deflection at a point along the beam length. Okay, so the main idea for that integration method, just recall that all you need is the moment functions. So what that means is a moment as expressed as a function of x. Okay, and as long as you have that, then you can do integration. If you integrate it twice and you apply the boundary conditions, then you can actually obtain an equation regarding the deflection as a function of x, or as a function of position. Although it is actually useful, and it is, let's say, fundamental, or a general method for solving deflection problems, but the mathematics becomes complicated when we have a moment functions that's more than one along the beam length. So right here again, I'm showing you the figure 8-7 in our lecture handouts, that when I say moment function, so along the beam length there is only one function of the moment. So right here we have a linear function, and right here we have a quadratic function of the moment. Okay, so from this x is equal to 0 to x is equal to L, we have one moment functions. But that becomes complex. The use of integration method becomes complex, or becomes lengthy in terms of its mathematics, is when we have two moment functions. Like, for example, right here. So because of these concentrated loads, then the moment just to the left of these concentrated loads will have a moment function like this, that's increasing, and just to the right we'll have another moment function that's decreasing. Okay, so recall that when we use integration, if we have one moment functions, if we use integrations, we get two arbitrary constants, right? So if you have two moment functions, then you get actually four arbitrary constants. Okay, so that becomes lengthy in terms of computations, and that's why there are also other methods for solving beam deflection problems, and one of those methods is this superposition method, which just simply means that the basic concept of this principle of superposition is that right here it says, if the response of a structure is linear, the effect of several loads acting simultaneously can be obtained by superimposing. Okay? Superimposing, or adding the effects of the individual loads. So in other words, if we have a loading condition or a beam condition that is something like this, let's say we have a simply supported beam, and we have a loading of, let's say, this loading, right, plus let's say we have another concentrated loads right here, and let's say we have a moment at this point. Okay, so how do we compute the deflection? Let's say we are going to find the deflection at the midspan right here. Okay, midspan. Okay, so the use of integration method would not be convenient, and therefore we need other methods such as this. Okay, so the principle, or the basic concept for this method of superposition is that we separate the loads. So that means that we separate the distributed loads, right? Okay, plus we separate another load, which is the concentrated load at this point. Okay, and the last one is these concentrated moments. So let's say this is our beam 1, right? Beam 1, and this is our beam 2, and this is our third beam. Okay, and this is our original beam. So what that means is that our deflection, okay, so the deflection is just simply equal to the deflection produced by this distributed load plus the deflection produced by this concentrated load plus the deflection produced by this concentrated moment. Okay, so that's how it works, right? So that's the concept of superposition method. Now, when we use this, what we need is the beam table or beam tables, like for example, given in this reference text. And actually you can find a lot of beam tables even in standards or handbooks, and also textbooks regarding mechanics of materials. Okay, so right here, by the way, this one is taken from this textbook, Strength of Materials by Paitel and Kisalas. And right here there is a beam table. Okay, so first, this first table it says deflection formulas for a cantilever beam. So that means that all the beam loadings right here, beam conditions are they are in cantilever beams. So which means it has a fixed end right here and a free end at the other end. Okay, another table is given, but this one says deflection formulas for simply supported beams. Okay, so which means that right here we have a simply supported, so pin and roller support, and there's a lot of beam loads configurations. Okay, so let's go through the tables. Okay, so right here is the illustration of the beam conditions. So let's say we have a cantilever beam, and that's loaded in the free end. Okay, and the equation for the deflection. Okay, so the entire equation anywhere along the beam length is given by this expression. So it says here. Okay, so here it is. It says here that the deflection can be solved by this equation. So px squared all over 6ei times 3l minus x. So that means that if you have the magnitude of p and you have the magnitude of ei and l, then if you want to compute the deflection at this, let's say we have a 1 meter length. So if you want to compute the deflection at 0.5 meters or 0.8 meters, then you can just simply substitute that in this expression. Okay, so the last two columns right here, you would notice that here it says deflection at B. So if you want to find the maximum deflection, and the maximum deflection actually occurs at point B, because we have here, this is point A and this is point B, so the maximum deflection occurs right here. So how do you solve that? Then you just use this equation, but the general equation is actually from this column. Okay, and the last column, this is the slope. Okay, so what's the slope at point B? And that's where the maximum maximum deflection occurs. So it's given by these expressions. So again, the general equation is given in this second column. Okay, now what if we have this condition, like we have a concentrated loads, but the concentrated loads is not at the free end, but rather it's somewhere in between the fixed and the free end. Okay, so we have two equations for solving the deflection. So just take note of these conditions. It says here that if x is between 0 and a, in other words, if we are trying to solve the deflection right here between 0, this is 0 and this is a, All right, so we will use this equation. But if x is greater than a, and or between a and l, which means that between, if the deflection that we are trying to solve is somewhere here between a and l, then we are going to use this expression. Now, what if we want to solve the deflection at this point? I mean, where the concentrated force acts, then I think you can just use either of the equations. Okay, so also just take note of the notations, or the let's say the symbol A. That's the distance from a fixed end to the concentrated force. Okay, and the fixed and the distance B is from the concentrated force to the free end. Okay, and right here we also have uniformly distributed loads for a cantilever beam. Now this one, this distributed loadings must be at this distance A, and the B is the portion where there is no loadings. Okay, now we are also given by these conditions that if you want to find the deflection anywhere, right, anywhere from 0 to point A, then we will use this equation. All right, and if we want to find the deflection from point A anywhere anywhere here in this unloaded portion, then we will use this expression. Okay, so again, you just have to substitute the value of x, and if you have the value of these distributed loadings and the flexural rigidity, then you can actually solve the magnitude or the value of the deflections. Okay, so right here in the third column, this is just the deflection at P. So that's the deflection at a specific point. Okay, and also at the last column, this is the rotation. Okay, so now let's go to the next table, which is for simply supported beam conditions. Okay, so let's start with this. Now, if you have a concentrated loadings that's not at the midpoint, then if we want to find the deflection anywhere here along this length, then we will use this expression, because the condition right here says here that the x is anywhere between 0 and A. Okay, and right here there is a specific value or a specific expression for the maximum deflection, and where that maximum deflection occurs, because the maximum deflection will not occur at the midspan, because this is not symmetrical loadings. Okay, so this is not symmetrical loading. This one is symmetric, and the concentrated loading is acts at the midspan. So that's why the delta max would be at the midspan. But if you have unsymmetric or non-symmetric loadings, then we will have a maximum deflection not at the midspan, and the value of x would be, or can be, solved using this expression. But if we want to solve for the center, then this table also gives us expression for the center. Okay, and also for the rotation right here. Okay, so I guess that's enough, and we'll do a couple of sample problems regarding this method of superposition. Okay, so for the first sample problem we have here, this one is taken from the textbook by Pytel and Kisalas, and this is sample problem 6.11. And it says here, compute the midspan value of EI times this deflection for the simply supported beam shown in the figure that is carrying two concentrated loads. Okay, so here's our beam conditions. We have two concentrated loads of 180, and we have this given distance. Okay, so recall that if we check the table, we don't have specific equations or formulas for the two concentrated loads, and therefore we have to separate the concentrated loads, okay, and use this expression. All right, so let's do that. So for the solution, okay, so first step is to separate the loads, and we can use this or actually we need to draw this one. Okay, and let's say this is our beam number 1, which carries this concentrated load of 100 pounds, right? 100 pounds, and the beam number 2 would be with regard to this 80 pounds. Okay, and what we need is also, we also need to label the dimensions. Right, so this is 2 feet from this given, and the distance right here, 4 plus 3, this is 7 feet, and the total actually is 9 feet. Okay, now for our beam number 2, this is 6 feet, 6 feet, and this one is 3 feet, and the total length of 9 feet. Okay, what else? Then I think we also need to draw the deflected shape, although this is not the exact, but probably something like this. And the midspan value would be right here. Right, so here's our deflection at midspan. It's deflection at midspan, and the distance is just, okay, this is 9, and therefore this is 4.5 feet. This is also 4.5 feet. Okay, so now let's solve for the beam number 1. Let's say this is 1 and this is number 2. Okay, so from the beam table, okay, here it is. This is, I think this is case. Okay, so if we try to number this 1, 2, 3, 4, 5, 6, right, 7, 8. All right, so case 8. So here's our beam conditions, and we can also we can actually use this if we want, but right here there's already given equations right here, because it says here that deflection at the center or deflection at the midspan is given by this expression if A is greater than B. Okay, so let's use this, but let's write first case, case 8, and the equation is or let's just use this. Let's try to use this general expression so that um, we can know the general procedure. Okay, and the deflection is, since we have these two conditions right here, we will use this condition because the deflection, we are I mean the deflection or the point x that we want to solve is greater than a. Here's our a, right, and here's our b. So it's greater than a, and therefore we will use this expression. Okay, so case 8 and a is greater than, or a is less than or equal to x, and less than or equal to L, and the expression is P over 6L EI, okay, times plus L squared minus B squared times x minus x cubed. Okay, so here's our expression, and if we write down our value of let's say a, what is a? A is 2 feet, and B is 7 feet. Okay, what else? What is L? L is 9 feet. And what's the value of P? So P is 100 pounds. Okay, so if you substitute all these values to this expression, what we get is a, and by the way, let's just write here, and also at x, so what's the position of the deflection where we want to solve is at x is equal to 4.5, right? So at x is equal to 4.5 feet. Okay, so since we don't have the EI, then let's just leave it that way. So EI times the deflection is just equal to, okay, what is P? Let's just write it here, 100, okay, times 7, that's our P, distance P, and 6 times the 9, the length. Okay, and then inside the bracket is 9 all over, right? So this is 9 all over this is B, 9 all over 7, okay, times 4.5 minus 2, and this is cube, okay, plus 9 squared minus 7 squared times this 4.5, okay, minus 4.5 squared. Okay, and what we get here is 946 pound-feet cube, and this is downward, of course. And I think I forgot also to write here from the beam table, beam 1. Okay, so this is referring to beam number 1. Okay, so now let's solve for this beam number 2. Okay, so for beam number 2, okay, so this is still at case 8, because it's still a concentrated load, but we will use this expression 0. So this is 0 is less than or equal to x, is less than or equal to a, and the equation is, okay, b times x, right, 6 all over 6l all over ei, and l squared minus x squared minus b squared. Okay, what is a? A is just equal to, A is equal to 6 and B is equal to 3. And A is equal to 6 and B is equal to 3. L is 9 and X is still 4.5. Okay, so if you substitute all the values, this will be 80 times 3, okay, times 4.5. Okay, here it is, and 6 times the length 9 times EI, but this EI is transferred to this side, and the length is 9 squared minus 4.5 squared minus the B. It is B 3 squared. Okay, and therefore this EI times the deflection is just equal to 1035 pound-feet cube, and the direction is still downward. Okay, so that's our EI times this deflection. This one should be delta 1, delta sub 1. Okay, so therefore the total, right? So therefore the deflection at midspan is, okay, so let's write here EI times this deflection, deflection at midspan is equal to EI times the deflection 1 plus EI times the deflection of the beam 2. Okay, so this is just 946, right? 946. They are both downward, so they are additive, plus 1305, and therefore the total is 1981 pounds feet cube, and the direction is downward. Okay, so EI, the midspan. Okay, so in review, we have here the beam conditions, and we have two concentrated loads. So the first step that we did was to separate the loadings. So we analyzed the beam as if it's only there's only one concentrated loads, because that's just our available tables. And also another one is if we have this concentrated load, this 80 pounds, and we just have to add this up. If we can find the deflection produced by this concentrated load and the deflection produced by this concentrated load, then we can just add that up, and that's going to be the total deflection at that midspan. Okay, so after that we went to the table and then select the case and also the conditions if applicable. Okay, and then we just substitute all the values and we obtain this magnitude 946. Okay, and we also did the same thing for this beam number 2. We just went to the table and we found out that it's case 8, but the conditions is this one, so therefore the expression or the equation for the deflection will be different from the ones we used in analyzing the beam number 1. Okay, so we just substitute all the values and we obtain this magnitude, and therefore the total deflection at the midspan is just simply the sum of the two, which is 1981. Okay, so you see how convenient this is, this method of superposition. However, it just really heavily relies on the availability of the tables. Other textbooks and standards, actually, they have more beam tables and other beam conditions, but right here we are just limited with this, and we'll just use this in our class. Okay, so in the next video we'll do 2 more sample problems regarding these beam deflections using the method of superposition.